Welcome back, and let's now talk about the parametric approaches. So as you can imagine, parametric approaches are the exact opposite to non-parametric ones. The idea is that this time we are making some assumption about the shape or the structures that the approximated function can have. And by doing this, we necessarily induce some bias in the predictions that we are making. But on the other hand, what we are doing is that we are fixing the number of parameters that the model can have. So this means that the number of parameters this time will not grow with the number of data. If we take again the same diagram as before, this time we are on the other hand of the diagram. So in the cases of a low variance, because the model will, the approximated function will only fit or follow what is given by the model and cannot have a huge variance. But it's necessarily inducing some bias, as I said before. And actually, you already know quite well a PDE algorithm with the Gaussian distribution. So here is a couple of reminders. So here, in this slide, we will talk about the univariate Gaussian distribution, and in the next slide, I will cover the multivariate one. So univariate Gaussian distribution use this notation with an n here to consider the normal distribution that takes as inputs value x, and that is parameterized according to two parameters, mu and sigma. Mu represents the mean of the Gaussian distribution, while sigma corresponds to the variance. And then we have here a normalization term to ensure that the integral of the Gaussian distribution sums to 1. And here we have the core term of the Gaussian distribution that involves the mu parameters and the sigma parameters. And so when you want to compute an approximation of a Gaussian of a distribution like a PDE or PDF, what you do actually is try to find the parameter value for mu and sigma according to the training set. So imagine you have those green points that are your training data points. What you will do is simply refer or report them in those two equations in order to compute the value for mu and the value for sigma. You will not be surprised that in order to compute the mean parameters for the Gaussian distribution, you need to compute the average value of the data point in your training set. The same thing goes with the variance here, because we simply compute the average square difference between the value of the data point in the training data set and the mu parameter. So that it's for the Gaussian distribution, and you can already know that when you have a Gaussian distribution with a large variance, this means that you will have a flatter but more spread out distribution. Again, it's because the integral needs to sum to 1, so if you cover a larger range, necessarily the values that the function will take will be smaller. And the opposite goes too, because if you have a smaller variance, this means that you will cover a more tighter space, but this means also that the value will go to the higher region. In the previous slide, we covered the univariate, and here we are covering the multivariate Gaussian distribution. So in this case, we have actually the input of the Gaussian that can take a multidimensional vector. So in this example, we have two dimensions, x1 and x2, and it's following kind of the same structure. So we have here the input x, which is now a vector because it has multiple dimensions, and we have mu and sigma, so mu for the mean of the Gaussian distribution, and sigma that represents the covariance matrix of the Gaussian distribution. Again, we have this normalization term because, again, the double integral over the different dimension of the space needs to sum to 1. And here we have same kind of terms with the exponential function that involves the mu and the inverse of the covariance matrix. And similarly to the previous slide, when we try to approximate a distribution with a multivariate Gaussian distribution, we are actually trying to fit the value of the parameter mu and sigma, again by computing the average vector of the training data points, and here by computing this function that will lead to the covariance matrix. So here, for instance, in this example on the side, you can find, or you can see in green, our training data points that are actually following a multimodal distribution, but we can still approximate it thanks to the two equations on the left that will lead to this distribution here. But you might now be wondering, how can we know how good is a model? And so for that, we use a quantity that is called the likelihood. So the idea is that what we want is a model to capture very well the probability of generating or observing a data point x within an interval. And so for that, we use, as I said, the likelihood, which measures the probability of observing any point x from our data set. And so the likelihood here, when we compute the likelihood, is that we assume that the data points that are contained in our training set are following the IID distribution. So identically and uniformly distributed distribution of data within our data sets. Not that the distribution we are trying to approximate is uniform, but more that the way we generated the training points by sampling this hidden distribution is identically distributed. And so the likelihood is simply, so here we have the capital X, that means actually all the points X in the training data set, and theta, which defines all the parameters of the model. So for instance, in the case of a Gaussian distribution, it will be the mean and the variance or the covariance parameters. And so the likelihood is computed by computing the product over all the points of the training data set, so the endpoints, and we will take the predicted value from the models that we will that is outputted for every samples of the data set, again following the parameters theta. But more likely, what we will actually compute is the negative log likelihood. The reason why we compute the negative log likelihood is because thanks to the negative term, we'll actually turn this maximization problem into a minimization problem, which then becomes very similar to minimizing the loss term, for instance, when we train a neural network. And usually in computer science, we are more used to minimizing quantity compared to maximizing ones. You will see next week that in evolutionary computation, it's the exact opposite. And the log is here simply for numerical stability. Indeed, when we start to multiply small probabilities, it's usually bad and leads to some numerical instability. So now let's try to use this notion of likelihood, and let's see how it's actually is actually used in Gaussian distribution. So when we try to do some Gaussian fitting, so computing the mean and the variance term in order to fit a given data distribution, actually what we are doing in the background without knowing it is minimizing the log likelihood or the negative log likelihood. And here is a proof, for instance, for the unit variant Gaussians. So as a refresher, we want to minimize the negative log likelihood, so which has this form here, and which is computed according to this term here. The reason why we don't have the product over all the probabilities, but the sum is because or thanks to the log term, which is turning every product into a sum. And you can find from the previous slide that the probability output of the Gaussian distribution is following this equation. So the likelihood or the negative log likelihood actually follow this equation here. And if that can be decomposed again thanks to the log term into this equation here. And you might know that if we want to minimize the quantity, actually the minimum will take place in an area where the derivative is actually 0. So we can compute the partial derivative of the negative log likelihood according to the two parameters, so according to mu and according to sigma. And so if we do this and we develop the math, we will see actually that the negative log likelihood, the partial derivative of the negative log likelihood according to the mean parameters will actually follow this equation and land to this result here. And the same thing goes with the sigma term. If you compute the partial derivative according to sigma of the negative log likelihood, you will end up with this equation. And if you solve it so that it's equals to 0, you will end up with this term. So you see here that the equations that we usually use for the univariate Gaussian distribution, but also for the multivariate Gaussian distribution, is actually just the closed form solution to the minimization of the negative log likelihood function. So then the question is, okay, is a Gaussian distribution enough for modeling densities? So if you remember this example of the flowers you might have collected during a walk in the forest, you can see that here we have a multimodal distribution. So we have kind of two clusters. And the issue is that if we fit a Gaussian distribution here, we will have this kind of result, which is definitely not satisfactory. And the reason is because by doing this, we are actually inducing a lot of bias, as I said previously, while maybe something a little bit less biased might be more suitable. But it's also sometimes more difficult to train, or will also be subject to a high variance. So the question is, can we find a better bias-variance trade-off? And in order to do this, what we can use is a mixture of models. So instead of having like one Gaussian that will try to capture all the density of the data, we can maybe use multiple models that all together will capture the different modes or the different particularities of the data distribution. And so the general definition of a mixture of model follows this form. So the value or the PDFs that we are approximating here, P of x, can be coming from the sum of some weighted PDF or multiple probability density estimations that we have done. And here we have the mixing proportion pi of k that is following those two constraints. So first of all, every quantity is lower, is between 0 and 1, and the sum of the mixing proportion sum to 1. Here, those two conditions actually are here just to ensure that if we compute the integral of p of x here, we will again be equal to 1. And a special case of mixture of model is the Gaussian mixture models. It's one of the most popular mixture models. And the idea is the same, so we can compute the an approximation of the probability density with p of x given a set of parameter theta, which is simply the sum of multiple multivariate or univariate Gaussian distribution and that are weighted according to the mixing proportions. And we follow the same condition as before. And in this case, we have as many couples of mu and sigma or covariance for as many mixed models we have in our mixture. So if we have k parameters, we will have k pairs of mu and sigma, but also we will have one mixing proportion for every single Gaussian distribution that we are considering in this mixture. So that is for the general consideration of parametric models, and in the next video we will cover GMM-EM, so the most famous way and the most practical way to train and fit Gaussian mixture models using the expectation maximization algorithm. So see you on the next video.